resonator. So I'll begin with an introduction to wavelength swept lasers, and then I'll describe a specific type of wavelength swept laser, which is the Fourier Domain Mode Locked laser. And then the motivations for this work of using a tunable novel reflector component in the FDML configuration, and that's based on a vertically coupled silicon photonic crystal cavity resonant reflector, and then a proof of concept demonstration using that component in the FDML, followed by the experimental results and the conclusions and future work. So wavelength swept lasers typically have a gain medium and a tunable optical bandpass filter. So when the laser modes are transmitted through the filter, they are amplified from the background and lays. And as the filter is swept, then that sweeps the instantaneous wavelength of the laser. So there's many applications for wavelength swept lasers. One of the main applications is swept source optical coherence tomography, which is a type of imaging technique that uses a frequency swept laser. The beam is split between a fixed path reference arm and mirror, and also onto a sample for imaging. Though both beams are reflected back then and mixed and sent to a detector. So that produces an interferogram with a period related to the depth of reflection. So with a sample with varying reflective interfaces and varying depths, that produces multiple interferograms, which is then Fourier transformed, and the peaks in the Fourier transform then relate to the depth of the reflection, and that's used for imaging. So to realize the wavelength swept laser, there's several types of configurations. One is a ring cavity configuration, has a SOA and a tunable Fabry-Perot filter. There's isolators in the cavity to ensure unidirectional lasing, but it could also as a linear cavity configuration. So again, there's a gain medium and a tunable Fabry-Perot filter. In this case, it acts as a retroreflector, so the angle that it reflects the wavelength determines the lasing wavelength, and that's tilted then with the MEMS to change the lasing wavelength. So there are fundamental tuning speed limitations in terms of lasing. One is the saturation limit, so there needs to be enough round trips in the filter transmission for the modes to amplify and lase. And there also is the post-filtering limit, so that's when the filter is swept by more than one filter width within one sweep. So if that's the case, then it will block part of the laser light and eventually stop lasing action. So those limitations were overcome with the introduction of the Fourier Domain Mode Locked laser, and that's a type of ring cavity laser. It has a gain medium and a tunable Fabry-Perot filter with the addition of a delay line placed in the cavity. And the idea is to synchronize the filter modulation with the round trip time of the light in the cavity. So in other words, the round trip time will equal 1 over the modulation frequency to the filter. And that overcomes the fundamental limits then, because lasing doesn't have to build up from spontaneous emission with each sweep. A full sweep is optically stored in the delay line. So it allows for extended continuous tuning range while maintaining high output power. And the current technology for FDML lasers have a focus on OCT. Because of the broad sweep bandwidth that can be achieved with the Fabry-Perot filters, it means that they can have high resolution imaging for OCT. And then since the fundamental limits are overcome, the maximum speed is determined by the maximum speed of the filter. So that's typically around 500 kilohertz for the Fabry-Perot mechanical type filters. So if they want to increase the sweep rates, then they normally add these buffering stages. And that's they'll dump the unusable part of the sweep, which is typically the backwards part, and then copy the usable part to multiply the sweep rate. But that complicates the circuitry of the laser. They're currently bulky and expensive, although they do have very high performance. There's isolators in the cavity to ensure the unidirectional lasing, which makes it difficult for integration. And that leads me on then to the motivations for this work, involving replacing the standard Fabry-Perot filters, which are used with a type of akinetic filter. So it's a filter that can be tuned with no moving parts, and it's based on a novel narrowband filter component in silicon 2D photonic crystal cavity. So it's a compact configuration, and it's compatible with CMOS processing. So there's a high QV ratio, which means there's low capacitance and less energy consumption during tuning and modulation. So to further describe that then, it's a vertically coupled photonic crystal cavity reflector. It's a 2D photonic crystal, so there's holes etched into the silicon substrate. A row of holes are removed and the innermost holes are shifted to form the resonant cavity. Light is vertically coupled from the waveguide, typically silicon nitride or SU8 waveguide. It's vertically coupled by K vector matching, as they're two different index match materials. And that then enables independent design of both the waveguide and the cavity for efficient operation. So at the resonance frequency of the photonic crystal cavity resonator, part of the light is reflected back then due to the Bragg effect. And that gives us then a narrowband reflectance peak. And that peak then can be tuned either thermally by heating in the cavity or by carrier injection depletion by doping across the cavity and the addition of PN junction. And so to characterize the photonic crystal cavity, using a broadband ASC source and looking at the transmitted output and also looking at the reflection, we can see that it acts as both a filter and a reflector and has multiple resonance wavelengths of varying bandwidths and reflectivities. If we apply a forward bias then to the PN junction, we'll cause local heating of the photonic crystal cavity, so we get the redshift of the resonance wavelength. And that gives us our tunable reflectance peak based on the silicon thermo-optic effect. So here we have about 50 picometers wavelength shift per milliwatt of applied power to the PN junction. So we use that component then in the FDML configuration. In this configuration, it's a linear cavity, so we have a fiber retroreflector, an SOA polarization controller, a 2-kilometer delay line, and the lens fiber then to input the light onto the waveguide and then into the photonic crystal cavity reflector. So as we're using the photonic crystal cavity as a reflector, that allows us to have it in a linear configuration. So that's attractive for integration, as we don't need any isolators in the cavity. So it's a highly multimode configuration. So there's about 10 to the 6 laser longitudinal modes within one reflector bandwidth because of the large cavity length here. And then for FDML operation, we'll apply a filter modulation that will match the cavity round trip time. But firstly, to look at the reflector tuning in DC steps. So just applying DC step voltage to the PN junction, we'll keep the fixed bias current on the SOA. And again, we see the redshift in the lasing wavelength, again, because of the silicon thermo-optic effect. And if we look at static reflector, so no tuning and just a fixed SOA bias, the highly multimode unstable lasing is evident. From the trick captures on the OSA there, we see unstable lasing mode groups. Also evident on the intensity dynamics, so we see kind of mode competition for gain and switching. They're unstable and large power fluctuations over time. So then we can apply the sine wave modulation to the PN junction. So for a 2-kilometer fiber delay would be about 20 microseconds round trip time, and that gives us 50 kilohertz for the synchronized modulation frequency. So at that frequency then we see that the sweep is starting to form. Parts of the sweep are still not active and unstable. So by stepping the modulation frequency then and looking at the output intensity, the average output intensity, we see it begins to decrease up to a maximum point and then decreases. So the frequency at that maximum point was determined to be the exact matched modulation frequency, which was 50.35 kilohertz. So at that frequency, then we have our FDML operation. The wavelength sweep on the OSA was stable with about 3.5 nanometers sweep range. The comb lengths present here are from the reflections from the photonic crystal cavity to the chip facet. And we can directly measure the laser phase with a 3x3 measurement. So this is a type of delayed self-heterodyne technique where we mix the laser output with a delayed version of itself to 2 inputs of a 3x3 coupler. And that produces then a beating pattern at the 3 outputs. They have a 2π/3 phase difference, which is inherent to the coupler. And the varying amplitudes of them then allows us to directly measure the laser phase. And that subsequently then allows for the calculation of the sweeping instantaneous frequency from that measurement. So that confirms then the sweeping instantaneous frequency in FDML operation with the 450 gigahertz sweep range at the matched modulation frequency of 50.35 kilohertz. And then the intensity stabilizes, has a stable amplitude envelope, which is cyclic and repeats with each sweep period and is stable over time. We can reduce the depth of the comb lines by reducing the reflectivities using AR-coated facets and angled waveguides. In this case, the modulator was a microheater device, so it was less efficient heating. So we get a reduced sweep range from that. If we set the fixed TLS close to that sweep, so it's a more simple heterodyne measurement, and look at the beating frequency over the time varying beating frequency, we again confirm the sweeping frequency. So possible applications for this, the current limitation is really on the swept wavelength range. So it would be limiting imaging depth resolution for swept source OCT, but a possible application could be surface analysis. Another application was the recent report of a similar type of configuration, and they used the heterodyne beating technique, which was the measurement I showed in the previous slide. And they use that to generate microwave waveform generation and use that then for high resolution imaging. So with the limited sweep range, this could be a possible application also. So to conclude, it was a proof of concept demonstration of an FDML laser using that novel akinetic reflector component based on silicon photonics. It was in a linear cavity configuration. The modulators are capable of megahertz sweep rates, which we did measure and had results for that. But there was a reduced sweep range because there was quite a roll-off on the modulator, but certainly are capable of those speeds. So at those speeds, the cavity length then can be scalable to match the modulator's speed. So with megahertz modulation, you'd be talking about meters length of a delay line. In future work then to improve those modulators, so get a better frequency response, which means we'd get more efficient wavelength tuning and wider tuning ranges. It could lead then to an integrated FDML laser, so could imply low loss waveguides on chip as the delay line, or alternatively a butterfly packaged with the fiber delay enclosed, which would ultimately lead then to a compact swept source laser, so to be capable of high speed and simultaneous multi-wavelengths from a single source. And finally, I'd like to thank the institutions and funding agencies. Thank you for your attention. Take any questions.
Sharon, could you please go back to the slide number 16?
16, yeah.